Hi learners, within this video we'll be discussing the correlation between the time response and the frequency response specifications. We have already discussed in my previous videos that time response is the variation of the output of the system with respect to time, and frequency response corresponds to the variation of system magnitude and phase with variation of frequency. We are having a number of time domain specification, that is the rise time, peak time, maximum overshoot. Then we are having the delay time and steady state accuracy. And there are a number of the frequency response specification like resonant peak, resonant frequency. Then we are having bandwidth, gain margin, phase margin. All these, all these specifications are being correlated with each other, and in order to establish a correlation between the time and frequency response specifications is the main target of this particular video. Resonant frequency and resonant peak, they are given by this expression. Here delta is basically the damping ratio. So value of the resonant frequency is dependent upon the damping ratio delta. Value of the resonant peak is also dependent upon the resonant peak, is also dependent upon the value of the damping ratio delta. So what is the correlation between time domain and the frequency domain specifications? As we have expressed, as we have derived the expression for the MP also, and there we could see that MP, that is the peak overshoot, that is also a function of the damping ratio. MR, that is the frequency response resonant peak, that is also a function of the damping ratio. So for satisfactory operation, MP should be around 10 to 15%, while MR should be around 1.4. In case MR is greater than 1.5 and the system is subjected to the noisy signal, then it may cause serious problems. So both MP and MR are indicative of relative stability of the system. That is the biggest correlation between them. Then moreover, as the damping ratio increases, MP decreases and get vanished when damping ratio is equal to 1. And after that, system does not produce any overshoot. MR will also vanish if damping ratio is equal to 0.707. And when damping ratio is very small, both MP and MR will be very large. That is also not desirable. That we can see over here, that as the damping ratio increases, MP decreases and get vanished when damping ratio is equal to 1. This is the graph of MP and MR. So this is giving you a correlation between the time domain and the frequency domain specifications. This is the graph of, this is magnitude versus frequency. This is the CT versus time. So this is representing the time domain specification. This is because this is involving the time response, variation of the output with respect to the time. Here we are having the magnitude response with respect to the frequency, and wherever the magnitude is becoming maximum, this is called the resonant peak, MP, and MR, sorry. And in the case of the time domain specification, this is MP, this is the peak value of the overshoot. Both MP as well as this MP as well as MR, they are function of the damping ratio. We can very well see that when zeta becomes equal to or greater than 0.707, this curve, it will become flat like this and the MR will vanish. Similarly, when zeta becomes 1 and above, even in that case also MP will vanish. So it means that both MP and MR are directly related to the value of zeta. For high value of zeta, both MP and MR vanish. They will disappear, as we can see from these two diagrams that we have just seen, that when damping ratio is equal to 1, after that the system does not produce any overshoot. And MR will also vanish if damping ratio is equal to 0.707. So that is being shown within these curves. When zeta is this is greater than 0.707, in this case, MR will vanish. And when zeta is 1 and above, even in that case, MP will vanish. So it means that both of them are correlated to each other. And when damping ratio is between 0.4 to 0.707, the resonant frequency and the damping frequency are comparable. But as the damping ratio approaches 0, both of them approach the value of the damped natural frequency. And when damping ratio is small, damping frequency is large and rise time is small. In this case, we are just looking at the correlation between the time domain response and the frequency domain response. Time domain specification is the damping frequency. Frequency domain specification is the resonant frequency. For low value of the damping ratio, we can observe that damping frequency is large and rise time is small. Resonant frequency is also large and the system has a fast response. So both of them indicate the speed of response. So both of them are also related to each other. And when the damping ratio is between 0.4 to 0.707, then resonant frequency and damping frequency are comparable. And as the damping ratio approaches 0, both of them approach the value of the damped natural frequency. So we can very well see this is zeta. With zeta, MP is varying like this. This is the variation of the peak overshoot with the damping ratio. And you can very well see similarly, we can have a similar variation of MR with the damping ratio. Then if these two graphs are showing the variation of the damping frequency with damping ratio, natural frequency with damping ratio, and the resonant frequency with the damping ratio. Again, we can very well see that both of them are approaching the same type of the curve. So it means that time domain specification and the frequency domain specification are closely related to each other. If damping ratio is changed, it will be affecting both the resonant peak as well as the maximum overshoot, which are the frequency domain specification and time domain specification. Similarly, as damping ratio is changing, it will affect the damping frequency, damped natural frequency, and the resonant frequency in the similar way. So this establishes the correlation between the time response and the frequency response. Thanks for the patience hearing. So thank you so much.